If there are no questions, let's do an example. So here's our input to our circuit. And it goes on in either direction forever. And it goes between, let's say, +1 and -1. And our values here are, we want it to have a period of 1. So let's see, this will be -1/4. And this will be +1/4. And this will be 3/4. And this would be 5/4. So this is 1, and this is 1/2. And we're going to use that as a voltage input. So we're driving this circuit with a square wave. And since the problem is already complex enough, I'll have mercy on you guys and give you a nice simple circuit. And to make it a little bit more interesting, we often find voltages. I'm going to have you derive for me the current. And so let's go about it step by step. Number 1. We're going to find our A sub n's and B sub n's. In order to do that, we're going to have to find our time period, which is, Charles? What's our time period of this waveform?
Is it just 1?
That's it. And so once you find the time period, then you kind of get that omega naught for free. Well, you can get the frequency for free. That's always going to be 1 over the time period, which will always be 1. And omega naught will always be 2 pi f. So in this case, it's 2 pi. And our A naught is pretty easy to determine. John, what's our A naught, just by inspection?
Is that 0?
Yeah, it's above the 0 as much as it's below the 0 axis, so its average value is 0. Now we got to do the hard work. A sub n. So that is always going to be 2 over the time period of the integral over any period of the function cosine n omega naught t dt. So I'm going to simplify that a little bit. 2 over t is just 2. And now I'm going to take the integral. Of course, the problem is that the function of t isn't constant over here, right? It moves around the place. So I'm going to have to break it up into smaller areas. Sabine, how would you break it up? What would your first integral be here?
My first integral would be from, is that, I think, -1/4?
Yeah.
1/4.
That's right.
Sine of n times our omega naught times t dt.
Yeah, so f of t in that region is just 1, so we'll multiply. This becomes a 1, so we just get our cosine of n omega naught t. And then our second integral, Sabine, I'll just have you finish that up since you started it off. We'll start at 1/4 and go to...
Our second integral, 3/4.
Yeah, that's it.
Which would evaluate to 0. So for the homework, we would solve for A sub n.
Well,
and B sub n.
I'm not so sure it evaluates for 0. I don't think it would.
From 1/4 to 3/4.
Let's see. And as long as we've got you on the air, what's the derivative? I'm sorry. What is the integral of cosine?
Sir,
Yeah.
on the second integral that you just did, wouldn't there be a negative in front of the cosine? Because
Oh, yeah, you're right. Thank you.
you.
Yeah, thank you. Thank you. Sabine, was that why you were saying it was going to be 0? because I had mistakenly didn't put the negative in there. When we multiply it by the function in that region, that function is -1. And so Jonathan is saying you got to multiply this by the -1, which is that negative sign. Sabine, tell me what the integral of cosine is. Is it?
No, I was just looking at it's sine.
Yeah, it's positive sine. And we'll
Positive
take
sine,
out
yeah,
this,
for the more specific.
and we'll take out
Can
this
you hear me okay through my mic?
almost perfectly. And we'll take out this n omega naught, right? If we were to take the derivative, it would come out. So to take the integral, we have to say 1 over n omega naught. I'll write that a little bit more cleanly. 1 over n omega naught times sine. And we'll evaluate that between t, since we're evaluating with respect to t, equals -1/4 to +1/4. And then from that, we'll subtract 1 over n omega naught sine of n omega naught t evaluated between t equals 1/4 and 3/4. Okay, that looks pretty nasty. Let's throw in some numbers and see what we get. So I see we get this factor, a common factor of n over omega naught. So let's pull that right out of those brackets. And now we have this massive thing of sine of n omega naught over 4. I think I'll draw it that way. Sine of n omega naught over 4 minus sine of n omega naught over -4, and then minus this thing, minus sine n omega naught, and we'll plug in our 3/4, and then minus a negative, which would be plus sine of n omega naught over 4. Oof. Any questions about that? That part is just plain old Calc 2.
Are we going to be able to just do this in the calculator or test if we set it there?
Dom, I hear you saying something, but your audio is getting garbled. Can you say it again slowly?
If we set up our integral correctly on the test, will we be able to just use the calculator to do this math?
As long as you get the correct answer, I'm fine with it. So I don't care if you use your calculator or not. As long as you get the correct answer, that's all I care about. And you'll find that way in grad school too, and you'll find that way through FE as well. You'll find that way in life as well. All right. So now let's say you could just stop it right there. And this, you can now calculate any value of a sub n by plugging in n into this. And that's, we could just say could stop here. Or if you think about it a little bit, does anyone remember what sine of -x is? Just as a little, aside over here. Sine of -x. What does that equal, anyone? Long pause. Think about it.
Negative sine of x.
Yeah, that's it. Negative sine of x. So that means we could make this a positive and make this a positive. And now we see, hey, this is the same as this, and this is the same as this. And so now we get 2
Sir,
Yeah, go on.
on the third term you have there, the minus sign, parentheses, why'd you end up with 2 omega naughts in there?
Yeah, I should not have. Thank you. Yeah, I should have had that. Thank you, Jonathan. All right. So now we've got this all over. You could stop it here, and maybe we should. But my point is that you can do a little bit more algebra, and with enough algebra, you'll eventually get this result. It does neatly contract into this, that any a sub n is equal to 4 over n pi times sine of n pi over 2. And you don't need to do all that. You could just stop here and you'd be fine. What's our b sub n's? Who's up next? Dom. Take a look at this and tell me what our b sub n's are. Our b sub n's are asking how much sine is there in that waveform.
Well, it doesn't start from 0. Looks more like cosine, so I'd say 0 sines.
Great. It's another way to look at it is that it's since our function is even, it can't have any odd components to it. It can't have any odd components, which would be our sines. And so now we found that was a lot of work to get all of our Fourier series coefficients. But there are the 3 of them. And that's all of them, an infinite number of them. So this is our step 1. Here's our step 2. Step 2 is just to convert it over. So our a sub naught term is the same thing as our little a sub naught term, which is 0. And to find our big a sub n terms, well, that's always equal to the magnitude of our a sub n minus j b sub n terms. But since our b sub n terms are 0, that's just the same as the magnitude of our a sub n terms. And so that's going to be equal to the magnitude of this. Well, this sine thing looks like it's going to bounce up and down, but I can keep the 4 over n pi out there. And now I just need to say it's the magnitude of whatever the sine of n pi over 2 is. So that's our a sub n terms. We can find our phi sub n terms by saying it's our angle of this, which is going to be the angle of a sub n. And I don't know what that is. That looks like it might be kind of complicated. I would probably have to just plug in some different values and look for and see if there's a pattern. There is a pattern, but there's nothing wrong with just simply saying it's the angle of, what's the angle of 4 over n pi going to be? It's going to be the angle of 4 over n pi plus the angle of sine of n pi over 2, right? The angle of this whole thing is equal to the angle of the first part plus the angle of the second part. And what's the angle of a real number? Of a real positive number? Phil? 0. It's always going to be 0. So that's just the same thing as going to be the angle of the sine of n pi over 2. Okay. So we've done step 2. Step 3. Step 3 is to find h of omega of the circuit. So let's see, we're going to have to draw this as let's do this using the same technique we use for Laplace. So this would be 1 over s. This is 1. And we want to find this I of s. How do we do that? Aiden, what would be your next step here? There's a lot of ways to do this. There's not just one.
I don't know, sir.
So what if instead of Vn of s, we said this is 2 volts? How would you find the current through this 1 ohm resistor? Pretend they're all resistors.
I would use a voltage divider.
Ah, you could, so you could use a voltage divider, but this isn't really directly a voltage divider, right? A voltage divider looks like this. You have a known voltage and you've got two resistors in series. But that's not quite what this looks like.
Could you do a source transform on that power supply and make it like a current divider?
Yeah, you could do a source transform here, and then you'd have a current divider, or you could do a mesh, or you could do a nodal. You'd have one node. You could do a lot of different things. But yeah, so that's a good approach to do a source transform. And then we'd have a V in of S. And Aidan, I'm going to keep you on the hot seat over 2. So here's our current source. And then tell me what else is on there.
So you still have the 2 ohm resistor. You'd still have the capacitor, the 1/S capacitor, and you'd have the 1 ohm resistor, and they'd all be in parallel.
That's it. Now, although there is a formula to do all this in one shot, you end up with nasty reciprocal signs. So I'm going to, and that can make algebra tricky. So I'm going to instead find these 2 guys, which are in parallel, and simplify that. And to do that, I'd say 2 in parallel with 1/S is equal to product over sums. I don't like this compound fraction, so I'll multiply top and bottom by S to get rid of it. And now I've got my new circuit. And now it's just a current divider. So let's see, tank. What's I sub S as a function of our input? What is our current divider rule? I'll start you off. It's equal to the input times.
It's the input times the one that you're not looking for. So 2 over 2s plus 1 over them multiplied together. So 2
Not multiplied together, but
added together?
added together. Yeah.
Okay.
All right. So that looks pretty horrendous, right? I would definitely multiply the top and bottom of this equation by 2s plus 1 to say that I of S is equal to Vn over 2 times 2 over 2 plus 2s plus 1. And the 2's cancel. And now I get IS is equal to Vn over 2s plus 3. And now I can find my H of S. It's defined to be my output. It's a triple equal sign. It's defined to be my output over my input. So what would it be? Who are you up to? Phil. Given that my I of S is equal to this, what's my transfer function here?
It's going to be I of S over, so all of that over, so Vn divided by 2s plus 3 over Vn. So then you can simplify that to be 1 over 2s plus 3.
That's it. And that's the answer to step 3. So now here's the tricky part. For Oh, actually, that's to find h of omega, right? Not h of s. So I should have written that instead. So h of omega is 1 over j2 omega plus 3. Just substituting j omega for s. Okay. So now I wish we had an extra screen. So now I'm going to copy this over. And I'm going to say that our A sub n's, here's our circuit again. We've got this circuit going into, this input going into this circuit. And we said that our A sub naught is 0 and our A sub n's are equal to 4 over n pi times the magnitude of sine of n pi over 2. And our phi sub n's are equal to whatever the angle of sine of n pi over 2 is. And we said our h of omega is equal to 1 over j2 omega plus 3. Okay, and armed with this, we're going to find out what our outputs are. So for some reason, I've noticed that cadets do not like to draw this table. And I really strongly advise you to do so. My first column is the harmonic we're looking for. And my second column is the corresponding frequency. So, I didn't write down what that fundamental frequency was. So this will have a corresponding frequency of 0, which is the same thing as DC. This will have a corresponding frequency of 2 pi, 4 pi, 6 pi, and so on. And then we're going to create our input phasor. So our input phasor, this is our capital A sub naught, which we figured out was 0. And this is just our A sub 1 at an angle of phi sub 1. And when you plug into this, 1 for each part, you come up with 4 over pi at an angle of 0. It's a real number. And then when you plug in n of 2 into this, we come up with 0. When we plug in n of 3 into this, we get 4 over 3 pi at an angle of pi, and we get 0 over here. And we could continue this on if we wanted to. This is where we're going to evaluate h of omega. So we're going to plug in our omega into this formula. So this would be 1 over 0 plus 3, which is 1/3. This would be 1 over j2. Now our omega is 2 pi plus 3. And this, we can continue to compute it down, but I'm going to show you a way to save a little bit of time. Remember, our goal is to multiply our input by our transfer function to find our output. It's just our input times our transfer function. So 1/3 times 0, we can see is going to be 0. This thing is going to be this complicated thing. This should be j4 pi plus 3. It turns out that this is about 0.1 at an angle of minus 76 degrees. But because we multiply it through, we realize that we're going to be multiplying through by 0 here. So it doesn't matter what these are. We know that the answer is going to be 0. This one we're going to have to figure out. So let's see, our omega is 6 pi. So plugging that in over here, we get 1 over j times 2 times 6 pi plus 3. So that would give us the complex number 4 over 3 pi at an angle of pi times 1 over j, let's see, that would be 12 pi plus 3. And that turns out to be 0.011 at an angle of minus 85 degrees. Notice how as we go up in harmonics, the magnitudes here drop off pretty fast. And that's because our transfer function here has this omega naught in it, so it tends to go down pretty fast. And it's also because our inputs have this 1 over n, so it also tends to go down pretty fast. So since our higher harmonics and frequencies of our input decrease and the circuit's a low-pass filter, these higher harmonics of our output drop like a rock. So all this is our step 4. And now we can do our step 5. And our step 5 is to add up the parts. So I of t is always going to be equal to, whoops. I of t will always be equal to this. And so on. And I should have said these are our outputs, so I've got our little prime symbols on this. And so for this particular example, it's equal to 0.1 cosine of 2 pi t minus 76 degrees plus 0.011 cosine of 6 pi t minus 85 degrees plus, and you can continue to add them up. And how many parts would you have to add? That's a judgment call. But seeing as how your magnitudes are dropping off by about a factor of 10 each time, I mean, your original waveform varied between -1 to +1. Your first part that's passed is 1/10 of that. Your next part that's passed is 100th of that. I would guess your next harmonic that you'd have would be on the order of 1,000th of that. And so if you're not worried about millivolts, you could stop there. And that's it. That's the secret of how to do this. So let's just review everything, because that was a lot. Big picture of what we're doing is we're taking an input, any periodic input to a circuit at all, and breaking it apart into a bunch of input phasors. Using the techniques, and that's what all this page was about. Step 3 is finding the transfer function of our circuit. And now step 4 is analyzing each phasor input independently. And you'll remember from an earlier section we did that since each phasor has its own unique frequency, we've got to analyze each one separately. And then we just add up the results.